Alright, in this video we're going to actually take a look at how to do some calculations involving solution concentrations. There will be an assignment online for this, so I would strongly recommend that you work through these problems with me before you jump in and try to do the assignment. We'll start with some simpler ones and then we'll get into some more complicated ones down below. So as you're watching the video, pause when and maybe copy the question down and then try to solve it yourself, and then just double check through the video to see how you're doing. As we do it, pay attention to significant digits in your calculations as well. So the first question we're going to look at is, what is the concentration of a solution that's made by dissolving 30.0 grams of magnesium chloride in enough water to make 2.00 liters of solution? So there's a little bit of nomenclature in here. Magnesium chloride, if you want to review your nomenclature unit, refresh yourselves on the rules for writing formulas, or you could cheat here and look in your data booklet at the page 6 where there are ions given there with their charges and formulas. So magnesium is an alkaline earth metal, so as an ion its charge will be 2+, so this is Mg2+. Chlorine is a halogen, so as an ion it's called chloride and its charge is Cl-. So magnesium chloride is going to be MgCl2. Keep that in mind. So we're going to take 30.0 grams of magnesium chloride and dissolve to make 2 liters of solution. What is the concentration of that solution? Now when you are asked to find a concentration, you can assume, unless it says otherwise, that it means the molarity of the solution. So we're going to find the molarity. There's two ways to do this. One way would be to use formulas, and I'll do the first question here with formulas, and then probably after that I'll resort to using just unit multipliers. So the first thing I'm going to do is realize that there's two simple formulas we have. One is moles and how it relates to mass and molar mass. So since we were given 30.0 grams of magnesium chloride, we could easily calculate how many moles there are. The second formula is our formula for molarity. Concentration is moles of solute divided by volume of solution. And we remember that that volume has to be in liters when you're finding a molarity. So the first thing I'll do is find the moles of magnesium chloride. So 30.0 grams divided by its molar mass, which I'll find from a periodic table. Looking up on a periodic table, magnesium 24.31 is its molar mass, plus 2 times chlorine, 35.45. So we have 95.21 grams per mole as the molar mass. With significant digits, we're going to have 3 significant digits. There's 3 digits here in the numerator, 30.0, and there's 4 digits on the bottom, so when you're dividing, we keep the smaller number of significant digits. So my calculator says 0.31509, etc. With 3 digits, I'm going to keep just the 3, 1, and 5. So there's 0.315 moles of magnesium chloride. Remember that zeros at the beginning of a number like this are not considered significant. Now we can calculate the concentration. The concentration will be the moles, 0.315 moles, divided by the volume in liters, and the question told us that there were 2.00 liters of solution. Again, we're doing 3 significant digits in the numerator, and we're dividing by 3 significant digits in the denominator, so we're going to keep 3 significant digits in our answer. So there'll be 0.1575, I'll write 0.158 moles per liter, or molarity. Okay, so that, or 0.158 moles per liter. Either way of writing it is acceptable. Now if you would prefer to use unit multipliers, then this is how I would have set this up. I would have started with my mass, 30.0 grams. The reason I'm starting with the mass is because I can do something with it. I can get rid of the grams and switch to moles of magnesium chloride. using the molar mass. 1 mole was 95.21 grams. Now that I've got the moles, I just need to get the per liter. Per liter means to divide by the volume. So I'm going to put the liters of solution down below. And unlike most unit multipliers where we're converting from one unit to another, in this one we're simply adding the per liter to the moles that we already had. So I'm just going to put a 1 on top as a placeholder. I'm not actually wanting to put any new units there. So my grams cancel, and I'm left with moles per liter. And there were 2.00 liters of solution. If you compare what I'm going to do here on my calculator to what we just did above, you'll notice we're doing the same thing. Mass divided by the molar mass, that gives us the moles, and then we're dividing by 2 liters, which is what we did here to get the molarity. So we'll get the same answer, 0.158 molarity, or 0.158 moles per liter. Question number 2 is similar but reverses that problem and therefore is actually a little bit more practical. Question number 2 is the kind of question that you would need to do in a lab setting or where a lab assistant might need to do this. Next week we're going to do a lab where you'll have to do a calculation like this, so be sure you're very comfortable with it. You're told you need to make 100.0 milliliters of a 0.200 molarity magnesium sulfate solution. To prepare the solution, you would use distilled water and appropriate glassware, which we'll talk about in a separate video. But you're going to use as your solute not just magnesium sulfate, but magnesium sulfate decahydrate. It turns out that the only solute available in the storeroom is the hydrated form of magnesium sulfate. Now keep in mind that in 1 mole of this compound, there's 1 mole of magnesium sulfate, so we're perfectly fine to use this, but keep in mind that when you're determining molar mass, you have to include the water in your molar mass because that's part of the formula that's here. So 100.0 milliliters, 0.200 molarity magnesium sulfate. What is the mass of the solid solute that you need to use to prepare that? So question number 2. We can do this again with unit multipliers or with formulas. If we were going to use the formulas, then we would work backwards. We would use first the formula C equals N over V, and we realize that we know the concentration, it was 0.200 molarity, and we know the volume, 100.0 milliliters. We would just have to convert that to liters. So we could find the moles of solute by taking C times V. And then once we knew the moles, we could use our other formula. Moles is mass over molar mass. And we know the moles now, and we know the molar mass. Again, remembering to include the water in the hydrate's molar mass. And we can find the mass by simply taking moles and multiplying by molar mass. So there's the approach using formulas. If we do the same thing this time using unit multipliers, one of the rules when I use unit multipliers is not to start my calculation with a unit multiplier. So when I look at the numbers that were in this question, we had 100 milliliters, there's a volume, that's not a unit multiplier. We have 0.200 molarity, that's the concentration. And remember that molarity means moles per liter. So this is actually 0.200 moles in 1 liter. So that's going to be a unit multiplier, so I'm not going to start my answer with that. Instead, I'm going to start my answer with the volume, 100 milliliters. So with unit multipliers, 100.0 milliliters of solution. And the first thing I'll do is get rid of the milliliters and switch to liters of solution. Now I'm going to use my concentration. I can get rid of the liters of solution, and I can switch to moles of the magnesium sulfate, okay? Or in this case, moles of magnesium sulfate decahydrate. And then finally, we can get rid of the moles and switch to grams of magnesium sulfate decahydrate. Okay? So the first first unit multiplier, 1 liter has 1,000 milliliters. Using our question, we had 0.200 molarity, which meant there was 0.200 moles per liter of solution. And finally, the molar mass, grams and moles, 1 mole of the magnesium sulfate decahydrate, 24.31 magnesium, plus 32.06 sulfur, plus 4 times 16 the oxygens, plus 10 times 1802 the waters. 1 mole is 300.57 grams. And if you again look at what we're doing here, you'll see we're doing the same thing you would have done with the formulas. First, switching to liters, our volume, multiplying by concentration, we're doing C times V in this first part of our answer here. Then we're taking that answer and multiplying by the molar mass to get the mass. So formulas, unit multipliers, they end up doing the same thing, but the unit multipliers, we didn't actually have to think about formulas or any algebra. Alright, so here we go. We have 100 milliliters divided by 1,000 times 0.2 and times 300.57. I need 6.0114 now grams. Now there's 4 significant digits in this volume. This is a perfect unit multiplier, so it doesn't affect my significant digits. There were 3 significant digits in the concentration, and there were 5 significant digits in the molar mass. So multiplying and dividing, there were 3 digits here, so I've got to keep 3 digits in my answer, 6.01 grams of magnesium sulfate decahydrate. Now notice, because there were 3 significant digits, it turns out that if our mass was less than 10 grams, we have 2 decimal places here. And so when you're in the lab choosing an electronic balance to use, you'd be perfectly fine to use the centigram balances, which measure only to 2 decimal places. You wouldn't need to use a milligram balance, which weighs to 3 decimal places in this particular case. Question number 3 is a more complicated multi-step problem. We're told that a solution was prepared by dissolving 10.0 milliliters of methanol. Methanol's formula is CH3OH. We're told its density is 0.789 grams per milliliter in 140.0 milliliters of water, whose density is 1.00 grams per milliliter. We can assume that the volumes are additive. That's important. We talked about in a previous video that volumes are not always additive in the real world. When you add 50 mils of methanol and 50 mils of water, you don't actually get 100 mils of solution. You'll get slightly less than that. But here we're going to ignore that small error, and we're going to assume that the volumes are indeed additive. So 10 mils plus 140 mils, we can assume will be 150 mils. So we're going to look for the mole fraction first. Then we're going to find, now this is new, the symbol, you see square brackets around a chemical formula. You might want to note this in your margin. That implies molarity. So what is the concentration, what is the molarity of the methanol in that solution? What is the percent volume by volume of methanol in the solution? And what is the molality of the methanol solution? So mole fraction, molarity, percent volume by volume, and molality based on that information there. Now, sometimes it's okay to just jump in and start solving a problem. Sometimes it's also a good idea to map out an answer before you jump in. We were given the volume of the methanol and the volume of the water, H2O. We were also given their densities and the fact that we can assume that their volumes are additive. If we know the volumes of the methanol and the water and we can add them, then we can put that together to find the volume of the solution. Keep that in mind. We were given densities, grade 9 science. We know that if we use density, we can convert volumes to masses. So mass of methanol, and using the density of water, we can find the mass of the water. Now what else could we do? We have molar masses, so if we know masses, we can use molar mass to find moles of methanol, moles of CH3OH, and if we use water's molar mass, we can get moles of water. Now let's stop and think about this. We were asked for the mole fraction of the methanol. Well, the mole fraction of the methanol will be the moles of the methanol divided by the moles of methanol plus moles of water. So we'll be able to find mole fraction now. We were asked for the molarity of the solution, the concentration. The molarity will be the moles of the methanol divided by the volume of the solution. The volume, of course, will have to be converted to liters to do that. So we have enough information there to get the molarity. We were asked for the percent volume by volume. So the percent volume by volume would be the volume of the methanol divided by the volume of the solution times 100. So we have the information to find percent V by V. And finally, we want to know the molality. The molality, if we look back at our definitions, is the moles of solute, so the moles of methanol, divided by the kilograms of solvent. Well, the solvent here is water, and if we knew the mass of water, this will be in grams. We just have to convert that to kilograms of water, and now we can go get the molality. So there we have it. We've got a plan of attack. We're going to take our volumes, use the densities to find masses. Masses can be converted to moles, and then we're basically home free to calculate everything we need. So, first thing I'll do is I'll take the 10.0 milliliters of methanol, and with one little unit multiplier, convert those milliliters to grams. There was 0.789 grams per milliliter. There's the density of the methanol. So we have 10 times 0.78, 10 times 0.789. Now, of course, you could do that in your head just by moving the decimal. And so we get 7.89 grams of methanol. That's the right number of significant digits, 3 digits, because there were 3 digits in our calculations. Do the same thing with the water. We had 140.0 milliliters of water. Its density is 1.00 grams per milliliter. So there's going to be 140 grams of water. Now we can convert to moles. We have 7.89 grams of methanol. Convert that to moles times, get rid of grams, switch to moles. 1 mole of methanol, its molar mass on a periodic table, 12.01 plus 16 plus 4 times 1.01, 32.05 grams. So we're going to keep 3 significant digits here, 7.89 divided by 32.05, 0.246 moles of methanol. We also wanted the moles of the water, so we'll take the 140 grams of water, get rid of grams, switch to moles. 1 mole of water is 1802 grams, and again 3 significant digits will be in this answer. So we get 7.77 moles of water. We're going to want the volume of the solution in liters. I'm just going to do some mental math. It's 150 milliliters, so 150 milliliters. We're assuming the volumes were additive. Get rid of milliliters, switch to liters, and we get 0.1500 liters of solution. And the last thing we said we would need was the kilograms of the water. So if we take 140 140 grams of water, and we get rid of grams, switch to kilograms, 0.140 kilograms of water. So we have now here all the things we need to calculate the different concentrations that we were asked to find. So let's tear that out, put it beside me here. So part A asked us to find the mole fraction of methanol in the solution. So the symbol for mole fraction is that scripted X of mole of the methanol is the moles of methanol divided by the moles of methanol plus the moles of the water, the total moles in the solution. So that's going to be, looking at the numbers I had below, 0.246 over 0.246 moles plus 7.77 moles. Alright, so when we add the numbers on the bottom, we're going to get an answer of 7.77 plus 0.246. When you add numbers, keep in mind that your answer gets rounded off to the number of decimal places in the question, so this would actually be 8.02, but that still has 3 significant digits. And when we divide now, we're going to keep 3 digits in our answer. 0.246 divided by 8.016, so 0.0307 is the mole fraction of methanol. Notice that it has no units because moles divided by moles cancels. Part B, we were asked to find the, where's my question, there it is, the concentration of the methanol, which is its molarity. So that'll be the moles of the methanol divided by the volume of the solution. So that's going to be 0.246 moles over the volume of the solution in liters, which was 0.1500 liters. So that means the concentration of the methanol is, keeping 3 significant digits in our answer, 1.64. And again, you could either say capital M for molarity or moles per liter. So there's 2 concentrations done. Part C asked us to find the percent volume by volume. The percent by volume. So that's going to be the volume of the methanol divided by the volume of the solution times 100. So the volume of the methanol was 10.0 milliliters. The volume of the solution, if we assumed that it was additive, 150 milliliters times 100. So 10 divided by 150 times 100, 6.67 with 3 significant digits percent. And then our last one was to find the molality of the methanol in the solution. Molality's definition is the moles of your solute, so the moles of the methanol, divided by the kilograms of the solvent, or the kilograms of the water in this case. So that's going to be 0.246 moles divided by the kilograms of the solvent, which was 0.140 kilograms, equals, with 3 significant digits, 1.76. And now you could say moles per kilogram, but that's really not how it's normally written as far as I've seen it. I would just put dash and then that scripted M, which is the unit molal. So we would say this was a 1.76 molal is how you would say that solution. the molarity that we had earlier, the way you would normally say that, you could say 1.64 moles per liter, but you could also say 1.64 molar if you were speaking it. That's probably what you'd say, a 1.64 molar solution, which means molarity. Alright, we have one last question to look at here. Question number 4. The lab assistant prepared 500.0 milliliters of a solution that was 0.200 moles per liter in sucrose, C12H22O11. Sucrose, of course, is table sugar. The density of the solution was 1.023 grams per milliliter. What is the mole fraction of the sucrose in the solution? What is the mass percent? And what is the molality? And if we maybe try that same game that we just played a minute ago, keeping in mind these units and their definitions. So mole fraction, we need the moles of the solute and solvent. Mass percent, we need the masses of those two things. And molality, we're going to need the moles of the solute and the kilograms of the solvent. So let's see if we can reason out how we could do this. We know the volume of the solution, it was 500 milliliters. We know the molarity of the solution. So right there, if I think of my formula, C equals N over V, we could use the concentration of the solution, the molarity, with the volume to find the moles of the sucrose. Moles of sucrose we could convert with molar mass to find, oops, I'm a little off the camera there, sorry. So volume with concentration, in our little formula C equals N over V, we could rearrange that to find the moles of sucrose. The molar mass of sucrose with the moles would let me find the mass of sucrose. Alright. We were also given the density of the solution. Now, what could we do with the density of the solution? Well, we know the volume of the solution. So if we use the density of the solution and the volume, we could find the mass of the solution. Mass of solution, mass of sucrose. The solution is made of sucrose and water, and there's a law of conservation of mass. So if I know the mass of solution and the mass of sucrose in the solution, we could put that together and we can go find the mass of the water that was in the solution. It'll be the mass of the solution minus the mass of the sugar that was in the solution. The difference would be the mass of water because of the law of conservation of mass. The mass of the water we could convert using its molar mass to moles of water, and mass of water we could convert to kilograms of water also. I think that that's everything we're going to need. To find the mole fraction, we'll have moles of sucrose and moles of water. That's going to let me find mole fraction. Mass percent, we need the mass of sucrose and the mass of solution. So there we have mass percent. Molality, we needed the moles of sucrose and the kilograms of water. So there we have the molality. So now we've got everything we need in our plan to go find all these different types of concentration. So let's do these different things right here. So we have the volume of the solution and the concentration. If you want to use your formula, C equals N over V, you could do that. Or I can use a unit multiplier. We have 500 milliliters of solution. And I'll convert the milliliters to liters. And then using the concentration, convert liters to moles of sucrose. Moles of sucrose. So 1 liter is 1,000 milliliters, and the concentration was 0.200 moles per liter. So we have 500 divided by 1,000 is 0.5 times 0.2 would be 0.100 moles of sucrose, C12H22O11. So there's the moles of sucrose. We can convert that to mass. So if I take that answer, 0.100 moles of sucrose, get rid of moles, switch to grams of sucrose. C12H22O11. So 1 mole, using my periodic table, we have 12 carbons, we have 22 hydrogens, and we have 11 oxygens. This is going to be a big molar mass, 342.34 grams, so that's going to be 34.2 grams of sucrose. Now we found the mass of the sucrose. We can get the mass of the solution using its density. So if we take our 500 milliliters of solution, get rid of the milliliters, we can switch to grams of solution using density. And the question told us the density was 1.023 grams per milliliter. We're going to keep 4 significant digits this time, so 500 times 1.023 is 511.5 grams of solution. And now, using the law of conservation of mass, we look back at our plan, we can take 511.5 grams of solution and subtract the 34.2 grams of sucrose. The difference has to be the mass of water that was in the solution. So 511.5 minus 34.2, there's 477.3 grams of water. Remember, when you're subtracting and adding with significant digits, you round off by the decimal places. So since each of those numbers had 1 decimal, I kept 1 decimal in my answer. And the last thing I needed, well, 2 more things, and I'm going to run out of room here. Why don't I just do some mental math? That's going to be 0.4773 kilograms of water, just dividing by 1,000. And now I can squeeze in the moles of water. 477.3 grams, get rid of grams, switch to moles of water. 1 mole is 18.02 grams. So we have 26.49 moles of water in that solution. Alright, so we've looked back at our plan above. We calculated everything there that we thought we would need, and we determined all this because we were very familiar with the definitions of the different units. We were looking for a mole fraction, so we needed moles of sucrose and moles of water. We were looking for mass percent, so we needed mass of sucrose and mass of solution. And we wanted the molality, so we needed the moles of sucrose and the kilograms of water. And we've got all of that now calculated down below, so now we can go do our different concentrations. So the first one, the mole fraction of the sucrose, mole fraction of C12H22O11, the moles of sucrose over the total moles. So the moles of sucrose plus the moles of the water. So that's going to be 0.100 moles divided by 0.100 moles plus 26.49 moles. When we add up those 2 numbers on the bottom, we'll keep 2 decimal places. So 0.1 plus 26.49, so 26.59 will be the answer on the bottom. That has 4 sig figs, and when we divide by the 3 sig figs on top. By that, we'll keep 3 sig figs in our answer. So 0.1 divided by 26.59, 0.00376 is the mole fraction. Now keep in mind, the two examples we've done of mole fraction in aqueous solutions, the answers for the solute is very low, and that's because in a solution, by far, the largest number of particles present will be water particles, the solvent particles. So the solute's mole fraction is almost always going to be very, very low in an aqueous solution. Part B, we wanted the mass percent of the sucrose in the solution. So that's going to be the mass of the sucrose divided by, now I could say here mass of sucrose plus mass of water, or since we calculated it, the mass of the solution, and then times 100 to get a percentage. So there was, there was 34.2 grams of sucrose, and there was 511.5 grams of solution. One thing that I think is obvious, I didn't say it earlier, is that when you're doing a mass percent, the mass units have to be the same, right? You can't divide grams by kilograms. So 34.2 divided by 511.5 times 100 is 6.69, 3 sig figs, percent. So that solution is 6.69% by mass. And then the final thing we wanted was the molality. So the molality will be the moles of your solute, the moles of the sucrose, divided by the kilograms of the solvent, so the kilograms of the water in this case. So that'll be 0.100 moles divided by the kilograms of water, which was 0.4773 kilograms. And that's going to equal 0.1 divided by 0.4773. We'll keep 3 significant digits, 0.2095, so 0.210. And then molality was scripted M. So there's the molality of the solution, 0.210 molal. So there's several examples ranging from very straightforward ones at the beginning involving molarity to a more complicated kind of questions with multi-step problems where we found that setting up a plan before we jumped in and answered the question, hopefully you found that helpful, and you might find that useful to do on a piece of scrap paper when you're doing this on a test question. Alright, so now you have enough information, enough practice, I hope, to jump in and start with your problem solving online. So good luck.